that my doors are both locked. I never do the one in the back, but I never lock. Keep it unlocked. You never know. It's probably for cleaner today. And the reason I'm checking this is because we do have a lockdown set today. The lockdown drill will be at 9 a.m. So what that means, if you, I think most of you have done a lockdown drill with me before. It means that we turn the lights down, I turn the screen off, and we stay quiet in our seats. It is a lot louder to go run 27 people to run there than to just stay quiet throughout the entire time. And so all of my doors are covered at all times. It stays black so you can't see. But if you do feel more comfortable running into a safe corner, you can. It's in the hole back over there. And that would be at what time? 9 a.m. So right around there.
Is this another?
That's not the answer.
No.
All right, so I'm gonna go ahead and look for. Hopefully somebody got 5 points off of this, which is half the march. Let's see. This is for Danny. I think I already checked yours. You didn't change anything? Okay, so 6. All right, give a round of applause. And I'll give you 1 point. Which means at this rate, next week you should get to 12. Next week you should get to 12. So before we get started, I'm gonna go ahead and review the bell work. I did want to say that I've been reflecting on the schedule. I know that a few of you would definitely prefer having not a test right after winter break on everything that we're going to learn. So there are 2 options. Option one is keep the current schedule as is, and I have that on the Google Classroom, what that is. Option 2 is to actually break Unit 4 up into 2 parts. Kinetics, Part 1, Transition Metals, Part 2. And then instead of giving 1 exam, I would be giving 2 exams. So basically half the material in each one, and the exam would be worth half weight instead of full weight. So like 0.5 in the grade book. It changes, option 2 changes the schedule a little bit. It gives more days for review and an additional day for a lab. But it would push our calendar back a week, meaning that we finish a little bit later in March than what we would otherwise. Either way, it doesn't really matter to me. I think both ways are fine. But the option 1 will be a little bit more rushed, meaning that you'll have a lot of content and you'll have it hanging over your head over winter break. Regardless, you will have a quarterly that will be going into quarter 2 after winter break. Regardless, that's happening. You can't revote. Well, so option 1 is keep the schedule as is. 1 Unit 4 exam on all lessons, and the quarterly on the 14th, which is the last class period before the quarter ends, but it still goes in for quarter 2. And the other option is to break Unit 4 into 2 parts. Just do kinetics as half an exam next week. So next week you'd have a test on the first 3 lessons, and then when we come back later, like a whole month later, from winter break, you'd have the second half on transition metals. So you have until tonight to vote. I guess you can't change your vote. So once you voted, that's what it is. So think about it carefully and vote by the end of the day. I'll announce on Google Classroom tomorrow which one won, because I won't see you on Friday. If you'll recall, I'm out of the building on Friday. Regardless, on Friday, it'll make your studying either studying laid back or studying because you have a test in less than a week as you're reviewing kinetics.
Do we have an extra lab if we choose option 2?
Yes. There's an extra lab in option 2.
Yeah, extra lab.
There's an extra lab and an extra review day because I would be breaking the test up into 2 parts. So it does an extra lab and an extra review day, but that does push the calendar back. So that's why I said it provides more time for review, which may benefit you at the end because more time for review means more time to like put connections together instead of rushing it. So I kind of like option 2 when I thought about it, but because I already told you like what the normal traditional schedule is, I wanted you to think about it and decide as a class. All right, so with that being said, let's go ahead and go over that bell work that last year the students found it pretty hard. This year, the maximum number I saw was 7 out of 10. pretty hard. So let's go ahead and take a look at it. Write an equation for the reaction of AuCl3 with H2O2. A few people got this confused with the rate equation. You're not being asked for the rate equation here. You're actually being asked for the chemical reaction, the reactants and the products. So this was AuCl3 plus H2O2 goes to, they tell you what the products are in the first sentence. Au plus O2 plus HCl. And so this is technically a pre-ACE or AS chemistry level question, just knowing how to complete and balance reactions. And so when you balance this reaction, it's not hopefully too difficult. I saw a few of you using fractions and that was fine. I came up with 2, 3, 2, 3, and 6. Yeah, as my numbers. And so double check to see what you got. You did not need state symbols here. They didn't ask for them. You don't need them. That was the first mark. The second mark, a lot of you ended up getting, not everybody proved it, but a lot of you ended up getting at least 2 out of 3 of the marks here. And this is to determine the rate equation of the reaction. And so the first thing to do would have been to look at the 2 reactions where you keep H2O2 constant. Look at what happens to AuCl3. When I double my concentration of AuCl3, I double my rate of production of O2. And so as long as you say that, that's enough for the mark. You don't technically have to show the math. So doubling concentration of AuCl3 doubles the rate when H2O2 is constant. So the order of AuCl3 is 1. That was the easy part. If you could say that the order of AuCl3 was 1, that would be 1 mark. The hard part, in my opinion, is coming up with the H2O2. Because in any of the experiments you choose, when you change the H2O2 from 0.5 to 1, the AuCl3 changes as well. So the way that I reasoned it was, and there are several different ways you could reason this and come up with the right response, is I thought, okay, let me pick these 2 experiments. And I could have easily chosen 1 and 3 or 2 and 3. It doesn't matter which ones I choose. And I said, okay, I already know that the order of AuCl3 is 1. So if I take how much this increases and how much that increases the rate out of the picture, how much would H2O2 affect the rate? So the way that I went through it with my calculator is I did 0.15 divided by 0.10, and that gave me my calculator. I think it's 1.5 though. 1.5. So this means, because it's first order, that the rate would be 1.5 times more from experiment 2 to experiment 3 from just the AuCl3. Yes, Ramon?
So on Cambridge exams, to explain your process, you can just like write down
the
like
math, or you can explain in words.
Okay.
Either is fine. And so the next thing I said was, okay, so I'm going to take 4.60 and divide that by 1.5. 4.60 times 10 to the negative 1, divide that by 1.5, and see how much is left in terms of the increase of rate. Because knowing that this one takes 1.5, the rest will be from the H2O2. And so I took 4.6 times 10 to the negative 1, and I divided by 1.5, which gave me 3.07 times 10 to the negative 1. And so then after that, I said, okay, so if I take out the effect of AuCl3, and now that would become, instead of 4.60 times 10 to the negative 1, it would be 3.07 times 10 to the negative 1. So the question is, then what is the effect of doubling H2O2 on the rate of production? 1 divided by 0.5 is the number 2. So looking at just the H2O2, now we have 1 divided by 0.5 equals 3.07, I revised the answer, divided by 1.53. and you get 2 equals 2, which means that the order of H2O2 is also 1. So the order of H2O2 is 1. And then for the third mark, what do we need to do? So 1 mark for the first order, 1 mark for the other one's order. What's the third mark here? They're actually asking us for the rate equation. So your final answer should be rate equals K AuCl3 to the first, H2O2 to the first. Now, many of you did come up with this conclusion. The hardest part of this question is being able to describe how you would come up with the order of H2O2. Whether you explain that with reasoning or you show it mathematically. That would be the most difficult part to prove here. So that's why I thought this was kind of a harsh question. But those were the first 4 marks. And some of you did knock it out of the park and get all 4 marks. Very good to those of you that did. Last year, I do remember this question was a struggle, which is why I set the mark so low. The next one, use experiments of specifically experiment 2. So this is one of those types of questions that if you don't use the results of experiment 2, they don't give you the mark. They're pretty strict here. So it says use the results of experiment 2 to calculate the value of the rate constant for the reaction. And so I'm going to go ahead and throw in my rate equation. And then I got 1.53 times 10 to the negative 1 equals K. Numbers are 0.1, 0.5, and K is 3.06. When I divide 0.1 and 0.5 by both sides. And so the units here are really spicy.
Yeah.
The answer for units, I'm going to give you the answer and then go back to the justification, because when I first saw it, I was like, wait a second. How is this possible? The answer is mole minus 2, dm to the 9, minute minus 1. Which does not at its outset make any sense at all, because the moles in the dm cubes, like usually it's 1, 3, like then 2, 6, then 3, 9. So something weird's going on here in finding the units. And I mentioned it a couple of times without giving it away. Back here. You're not given mole dm cubes. You're not given concentration and molarity here. You're just given a volume of a gas. So the actual units for rate here is just dm cubed minute minus 1. So what does that mean? If they told you the units are dm cubed, and why is dm cubed not mole dm cubed? It's not a concentration, it's not aqueous. It's a volume of the gas. And so in order to find the, and so that's what I said, this is a tricky question. To find the units, you would plug in dm cubed minute minus 1 for rate, and then it would be K, and then the same thing that we typically do, which is the mole
Like I'll get
dm minus 3
$2.
to the here. So then solve for K, which means divide both sides by the what comes next? Distribute this 2, right? So you have this. dm cubed minute minus 1 over mole 2 dm minus 3. How do we get our final answer here? These numbers at the bottom have to come to the top to make it one line. So this would end up being mole minus 2, because it's mole to the second on the bottom. This would become, this would become dm positive 6 at the top, right? If this is dm minus 6 at the bottom, it becomes positive 6 at the top. Or 3 minus 6, which is dm to the 3 minus 6 is 9. And then minute minus 1, which is the answer given in the mark sheet. So that was a trick. That was a trap. Watch your units carefully. That one tripped, I think, everyone up. I didn't see anybody get that point. And I unfortunately didn't expect anybody to get the point. Sadly. Because it's one of those you had to watch it really carefully to like catch what was going on. All right, next question. This one I actually thought overall, at least the first part, was some of the easier marks of this spell work. The first question here says the reaction has a constant half-life, meaning every amount of time is the same. And they ask you to explain why. Well, they tell you here the order's 1. And if the order's 1, then the half-life doesn't change. So literally to get the mark, all you have to say is because the reaction is first order. No more words. You don't have to say why it's first order. You just have to say that it's first order because they're presenting you with that information. Yes.
Seen by first order, are we referring to the
The overall reaction.
the overall reaction order or just with respect to one reaction? I mean, I know in this scenario there's only one
The
reaction.
overall reaction order.
The overall?
Yeah. Okay. So use the information in this question to show that the half-life is that number. This is actually one of those that they're telling you the answer they're looking for, which is nice. You have to know the formula though. The formula is T1 half equals 0.693 divided by K. That's the formula you have to use to solve this. So it would be 0.693 divided by this. 2.50 times 10 to the negative 5. And then when you do that, you actually get that answer. So basically, you writing these two numbers is all you have to do for the minimum amount of marks. 0.693 divided by 2.50 times 10 to the negative 5. It gives you that number. And then this last question might have been a little bit spicy, but I don't think it was impossible. Unfortunately, I'm guessing that a lot of people ran out of time and didn't get to solve this one because you were stuck over this question. 8 times 10 to the negative 6 moles of cisplatin, which we'll learn what that is when we do the second half of the unit, are added to 100 centimeters cubed of water. Calculate the time taken for this to fall to this concentration. So the first thing you need is your initial concentration. How could we figure out the initial concentration of the cisplatin? You have to do concentration as moles over dm cubed, right? We've got the moles, 8 times 10 to the negative 6. And the dm cubed, they didn't give us dm cubed, they gave us 100 centimeters cubed. So we have to do what? We move that over 3 spots, and it will be 0.1. So this would be 8 times 10 to the negative 5. That's the initial concentration. And they tell you, calculate the time taken for this to fall to this concentration. Anybody have a suggestion on what we could do to figure that out? Isa?
I'm thinking we can find the rates of the initial concentration of one, then subtract the rate of the other one. Like, you have both
We
concentrations.
have the time of the half-life.
Oh,
We know how much time it takes to get to half. So really the question is, how many times do I half this to get to this amount? Ramon?
So what I'm thinking is that we do the equation, what's it called, half to the t, and then
Oh, you could. And I have both justifications. Like I have the brute force it method
Yep.
and I have the equation method. You could solve it either way. Isa?
can we just divide the molarities and then just multiply them?
That's the brute force method. So because you only will be given in this class whole number half-lives, thank you, Cambridge, you could literally do the following. Do 8 times 10 to the negative 5 and keep dividing it by 2 until you get to this number. Go ahead and do that in your calculator. How many times would you need to divide 8 times 10 to the negative 5 by 2 to get to that value, 2.50 times 10 to the negative 6? I did it, but I'll show my reasoning. Divide by 2 once, get whatever that is. which would be 4 times 10 to the negative 5. Then divide that by 2 again. That would give me 2 times 10 to the negative 5. And divide that by 2 again. Just keep dividing it by 2. That's 1 times 10 to the negative 5. Divide that by 2. Because we're looking to match this number. 5 times 10 to the negative 6. Divide that again by 2. And it's 2.5 times 10 to the negative 6. How many times did you have to divide by 2? 5 times, right? Which means that 5 half-lives have passed. We know the amount of time for every half-life. It's that amount of time. So you would do 2.77 times 10 to the 4th multiplied by? Multiplied by 5. And that will give you the answer. Yes.
On the scenario in which it's not a whole number, can we just use the variables?
You got enough time for that? So I can show you the other method real quick. If we had been given a non-whole number, and even, to solve this question, we could have alternatively used Ramon's suggestion, which was goes to the equation, which is A equals AO 1/2 to the N, where N is the number of half-lives. So then how would we use that? Your initial amount would still be 8 times 10 to the negative 5. Your final amount, we also know that. It's 2.5 times 10 to the negative 6. So you would have, so this is alt method. If you know logarithms, it'll work. If you don't understand logarithms properties, don't choose this. Okay, so then we're going to say that our initial is 8 times 10 to the negative 5. This is 2.5 times 10 to the negative 6, and then 1/2 raised to the power of n. The next step would be to divide by the number in front, which is 2.5 times 10 to the negative 6, because this 1/2 is got the n attached to it. So you would divide by this number in front. So you divide both sides by 2.5 times 10 to the negative 6. And that gives me, because I did work this out, it gives me 0.03125 equals 1/2 to the n. And now you have possibly a problem, possibly you know how to solve this. You have n in an exponent. You need to figure out what n is. What is the logical next step? Add ln to both sides. So ln of 0.03125 equals ln of 1/2 to the n. The natural logarithm. Then this will allow you to get n out of the exponent because you will put n to the front. That's one of the logarithm properties. And so you have ln 0.03125 equals n ln to the 1/2. And to solve for n, you would divide both sides by ln to the 1/2. And I worked it out on my calculator. I just put ln 0.5 in my calculator. And the answer will be n equals 5. It will give you the same answer. So if you want, you can go the formula route. It works for any time frame. You don't have to then do this. This is called the brute force, method, where you just keep dividing by 2 until you get the answer. And for the purposes of what we have to do in this class, that works. But if you were to go into more advanced science, you would choose to do this method because more advanced science requires more advanced mathematics as a result.
What do you do with the 5?
Multiply by, because that's the number of half-lives. This is the amount of time in each half-life. So still you do this second part. Yep. All right, so do you have to do this method for the purposes of A-level chemistry? Cambridge says, nah, you don't got to do it. You can brute force it. But in a physical chem class, definitely you would be choosing the higher level math method. Because it works for everything. All right, so last lesson of kinetics today. Unit 4, lesson 3. Today we're going to be going over reaction mechanisms. You should be familiar with the word mechanism in this class. We did mechanisms back in AS chemistry. And so reaction mechanisms and rate of reaction and catalysts. So I think that this lesson will answer a lot of the questions you have been having with orders of reactions. Because remember that we said back in lesson 1 that you can't match the coefficients to become the orders unless you have a one-step mechanism. So what happens when you have multi-step mechanisms? That's what we're going to look at today. I don't know why this keeps. All right, so let's get started. There's a lot of standards, but technically all of this is one standard. It's for a multi-step reaction. Suggest a reaction mechanism that is consistent with the rate equation. This is actually, I think, the hardest standard in Cambridge. The hardest learning objective is when they say suggest. Why is suggest the hardest objective in general? Critical thinking. There is not one right answer. There's multiple different possibilities that could work. Suggest means you come up with this. So I'll try to teach you how to do that. The next, predict the order that would result from a given reaction mechanism and the rate determining step. Deduce a rate equation using a reaction mechanism. Identify an intermediate or catalyst. Most people say that this is the easiest objective for anything that you ever do. Identify. Because identify just means you know what it is. Whereas suggest means higher level thinking. So identify an intermediate or catalyst and identify the rate determining step. And then the second half of today's lesson is catalysts. We have already went over catalysts in AS chemistry, at least the first objective, and we'll be going over the other two objectives shortly. Hello, this is Miss Wheat. Yes. Okay, sure. A moment to go to Miss Hawkins. Just for a minute, she said. And so we're going to review homogeneous and heterogeneous catalysts, but then we're going to talk about how they work. So this is that lesson that I told you I was going to tell you how do heterogeneous and homogeneous catalysts work. We're going to go over that today. We're going to look at heterogeneous catalysts, and we're going to look at homogeneous catalysts and how they actually work, when they work, why you would choose one instead of the other. And so let's get to it. A lot to go over today, a lot of objectives, but that means most of the objectives are very fast in comparison to the math objective we were doing before. So not so much math today. Reaction mechanism. So if you'll recall in organic chemistry, which is not too far away, after we finish the Unit 4 exam, we go straight into organic chemistry for the rest of the school year until we're done with content. So in the organic chemistry segment of the course, we learned about something called mechanisms. Mechanisms were how the reaction takes place. And there were some mechanisms that were one step. And there were some mechanisms that were two steps. You may recall the most famous ones were SN1 and SN2. Actually, one was a one-step reaction, one was a two-step reaction. And so we have seen mechanisms before, but now we're going to look at them in inorganic chemistry, which means not necessarily carbon molecules. However, you could look at it with organic chemistry. But these are the steps of the chemical reaction. There are very few reactions that actually occur in one step. Most occur in multiple steps. And this is an example of one. So write a line here for yourself. This would be the first step of this reaction. Notice it says flow. This would be the second step of this reaction. Notice it says fast. And then here it says your overall reaction. So do you remember when we were learning SN1 reactions that I mentioned that the first step was really slow? Because in an SN1 reaction, like I'll just throw one up here. In an SN1 reaction, OH minus is a nucleophile. Do we remember these words?
No.
Nucleophile.
That means it wants to like get electrons or something, right?
It means it wants nucleus. Nucleophile means wants nucleus, wants positive charge. It's negatively charged. Bromine is also a nucleophile, but it's a better leaving group. And so bromine, we call this the leaving group. Yes, organic is creeping. It's going to be creeping back into the course. And so until bromine decides to leave until that bond breaks, OH minus cannot take its spot in an SN1 reaction. So if you'll recall, we said that the first step was very slow, that the leaving group leaves first, right? And then you would get this as an intermediate. This would be called an intermediate. Once the bromine leaves, we had an intermediate. Intermediate means that it's not our final product. It's something along the way. It's the product of the first step. And then the OH minus would come in and go ahead and connect with that C plus, make a bond, and then you'd have your final product. This is something that we did back in AS chemistry. I know it has been a little while. But I think it's important to go over that idea because it has everything to do with what we're doing here. Notice in this reaction, in the slow step, you make F. In the fast step, F is used to make your final product. But F is not part of your overall reaction. So F would be called what? An intermediate. So this is an intermediate. The next thing I want to bring up, when you put your reactions together, your different steps of your reactions together, it should all add up to your final product. Meaning that if I have an intermediate, it's going to cancel out. And then everything else should add together. So I have an NO2 here and an NO2 here. How many NO2s are in my product? 2 of them, right? I have one F2 in my product. I have 2 NO2Fs here, 2 NO2Fs in my final product. And so all of my subsequent steps will add up to my final reaction. The last thing I want to bring up here is notice there says K1 and K2. What do you think that means? The rate constants, go ahead. The rate constant changes from the slow step to the fast step. So this is the rate constant of the first step. And this is the rate constant of step 2. So remembering back to SN1 reactions, we said that the reaction could not proceed until the leaving group left. That means that is the slow step. And the slow step always determines the final rate of the reaction. It is called our rate determining step, which you're going to see mentioned many times in this lesson. The fast step happens right away. So as soon as the slow step finishes, the fast step, it just goes. And so this will be what we call our rate determining step. And I'll write this down in a little bit. So lots of information to go over. On the next slide, you're going to see some of these definitions show back up. Looking at reaction mechanisms, we can see the following from this last one. Fluorine did not show up in the overall reaction. It was made in the first step and used in the second step. It is called an intermediate. Anything that's made in one step and consumed in another step is an intermediate. So anything made in the first step or any step and used in a subsequent step is known as an intermediate. So it'll always cancel out. The other type of substance that will always cancel out and will not show up in your final reaction is something called catalyst. A catalyst would be shown in the reaction side of one step and the product side of another step, which means that if it shows up on the reactant side and then it shows up on the product side, you're going to cancel it out. What is the purpose of a catalyst? Speed it up. So a catalyst will show up in reaction mechanisms, but it will not be in your final answer for a reaction because it's going to be produced at the end. And the next thing that's really, really important, the overall order of your reaction is completely determined by your slow step. goes by another name. It's called the rate determining step. That's what Cambridge will call it. Determines your rate of reaction is the slow step. Even your coefficients for your orders will be the same as in the slow step. So that means I actually know what my rate equation is going to be for this reaction. Yes.
Is there only one rate determining step?
Yes. There would be the slowest step would be the rate determining step. So if there were two slowish steps, the slowest step is the rate determining step. And so I can actually completely predict my rate equation from the slow step. Rate would equal K, and then just the reactants that are on the slow step. So rate would equal K, NO2 to the first, and then F2 to the first. If I know I have my slow step, then I also know my orders of my reaction because it's determined just on the concentrations of these and the amounts of these reactants that determines my rate of reaction. Which is why you can see here, this says 2 NO2, but our order of NO2 is only 1 because I only need one of them in my slow step. That's the idea. So that's some of the vocabulary we need to go over. We're going to take a look at some questions to help us further understand this vocabulary, and then we're going to get to the suggest step that I told you was a little bit scary. But I know you all, you can handle this. All right, so practice question. Bromoethane reacts with sodium hydroxide to form ethanol. A proposed mechanism is the following. Experiments show that the reaction is first order with respect to bromoethane and first order with respect to OH minus. Can you first state the rate equation? Rate equals K bromoethane to the first order. So CH3, CH2, Br, 1. That's good enough, 1. And then OH minus to the 1. Is that good? Is the rate, and this is a question that I've seen show up in a bunch of the textbook questions. How is the rate equation consistent with the mechanism? What do we mean by consistent? Does this mechanism prove this rate equation? Are they in line with each other? Does it make sense? That's what it means by, is it consistent? The answer is yes, because the coefficients of the slow step are the orders. So yes, because the coefficients of the reactants in the slow step are the same as the order. You're just saying why it makes sense. And then what type of reagent is OH minus? I kind of said it just a little while ago. What type of reactant is this? It's a nucleophile. That's what OH minus, it wants the nucleus. It is a nucleophile. Which means this is a nucleophilic substitution that's being shown here. Which this actually should take place via SN1 because it's a primary. Primary. So, but this came from a, I think, workbook that I found from Cambridge. Let's try another. This is also from a Cambridge workbook. Given the following reaction, that's the reaction. The rate equation is rate equals K, BrO3 minus, Br minus, H plus second. A proposed mechanism follows. Question is, first of all, what is the overall order for the reaction? 4. Because it's just 2 plus 1 plus 1. And then the next one, this is also, like I said, from a Cambridge workbook, not from a Cambridge test question, but they do ask this relatively frequently in the textbook questions. Why is this mechanism consistent with the rate equation? Because if I look at the flow step, that looks like it's HBr to the first and HBrO3 to the first. So how is this consistent? Why is the order 4 and not 2? Because these actually split up. This is actually H plus Br minus plus H plus because they're acids. BrO3 minus. So these H pluses are actually 2 of them, right? In the slow step, because H plus and another H plus would be 2 H pluses plus Br minus plus BrO3 minus. So all the ions combined would be to the 4th order. Yes.
What's the Ka of the acid matter in this situation?
The equilibrium constant.
Of the acid.
This works because like this order is what it is because these are strong acids. So the K is infinity. For strong acids, you would break it up completely. So then why is this mechanism consistent with the rate of reaction? There are 2 H pluses, 1 Br minus, 1 BrO3 minus in the reactants of the slow step. So that would give you the order of 4. Which completely, like I said, determines the rate. So that's all you really need to say here. On the next 2 slides, we get to actual Cambridge questions from paper 4s. Yeah.
These types of questions, do we always focus on slow steps? No.
The reactants of the slow step. The reactants of the slow step tell you the order of reaction. Yes, Lisa.
What happens if there's a catalyst or one of the other ones?
Let's see as we look through more questions. So let's check the next one. This is actually from paper 4. The next 2 questions, you can tell by the way it's written. This comes from a Cambridge exam question. A 4-step mechanism is suggested. A 4-step mechanism. And they tell you the 4 steps between hydrogen peroxide and iodide ions. Step 1 is the rate determining step. What did I say that the rate determining step was? It's the slowest step. And that's actually all you have to say for the point. The slowest step of the mechanism, or the slowest step of the reaction. The slowest step. 3 words gives you a mark. You do not have to over-explain it. You don't have to over-explain it. State is also what we consider to be an easy objective. State just means tell us. Tell us what you know. Tell us you know what this means. Use this mechanism. So this one's a little bit more complicated, but I think we can handle it. Use this mechanism to construct a balanced equation for this reaction. So how would we come up with an overall reaction from this mechanism? Remember, all the steps at the end have to add up to your final reaction. So the idea is you would take out intermediates first. And what else would I want to take out? Take out any intermediates and take out any catalysts. And then add up everything else. So can I spot any intermediates I need to take out? I see IO minus first. You see IO minus? It's made in step 1 and used in step 2. That means it's an intermediate. What else can I take out? What's made in one step and used in another?
HIO?
HIO. 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 Why would we take out water?
It's a hydrogen and hydroxide are being polinols, right? Hydrogen ion is being used in step 2 and the hydroxide ion is being used in step 4.
Mm-hmm. Yeah, maybe get to that in a moment. Are there, because you would figure that out later on typically.
And I mean, I'm asking, like, where does the hydrogen ion come from? Well, I'm guessing.
Let's wait till we finish it. Are there any, well, hold on, there's another intermediate.
Yeah,
No,
Like,
OH minus is an intermediate, so no, it's not gonna cancel it out. OH minus is made in step 3. OH minus is used in step 4. Right? You have to cancel it out. Anything that's made in one step and used in another, you have to take it out. Are there any catalysts here? I don't see any personally. Yes, Atzel.
How could we tell if we see a catalyst?
It would start on the reactant side and end on the product side. So it's the opposite of an intermediate. An intermediate is made in one step and used in another. A catalyst you start with and then produce it at the end. Yes,
as the intermediate has to be like used and like
it has to be used as part of the reaction.
on the
In a
products
subsequent step.
that- Like so it can
It's
the consecutive.
made, not consecutive.
not consecutive.
Yes.
So the hydrogen ion is a catalyst. It's not a catalyst. I have an arrow wrong. Never mind.
Take out intermediate catalysts. We don't have any catalysts here. We just have 3 intermediates that we already took out. Add up everything else, meaning all of these should be added up, whatever's left, and that would give me my reactants. So I have H2O2 plus 2H plus. So far, following me? Plus 2I minus. Good so far? And what are my products? I2 plus 2H2O. And that's our final reaction. That will give you 1 mark. Does it make sense how I did this? Yes, Francesca. Yeah, using Scan Show Go. So next question is deduce the order of the reaction. How can we figure out the order? Is there any information to figure out the order? Coefficients of what? Oh, coefficients of the slow step. Coefficients of reactants in the slow step. Were we told that? Did they tell us what the slow step was? Step 1. It says it here. It's step 1. So then order of H2O2 is what? I'm sorry? I don't have that many passes left right now. I'll write you one. Well, it's going to have a coffee mark on it.
That's like getting your signature.
That does make sense. Is it really Miss Fleet? Yeah, there's a coffee mark. There you go. Okay. H2O2, are we good with the order being 1? I minus, are we good with the order being 1? H plus, are we good with the order being 0? Go ahead.
Is this one that they could give us the like equation and make us create the mechanism? Or not create
Oh,
the
yeah.
mechanism?
Yes,
Yeah.
that's coming. For some, fun for some.
I mean, it's so fun.
Yes, we'll be doing that. We'll be coming up with our own mechanisms shortly. Point here. H plus has an order of 0. I remember Luke, you asking about that yesterday. How can something have an order of 0? If there was none of it, the reaction wouldn't happen. That's true. If there was none of it, the reaction wouldn't happen. But as long as there's some H plus, it reacts immediately, is the idea. And so this is the slow step. It determines the rate of the reaction. The K of this is much smaller than the K of everything else. So what that means is that the rate is completely dependent on what's happening here in step 1. As long as there's any of the other reactants necessary for the reaction goes almost immediately. And so that's how you arrive at an order of 0. That's why I said wait for mechanisms, and I can explain it better. Yes.
When you're finding a balance equation in your crosshabs and your medians, does it have to be like made in one step?
It doesn't have to be the exact next step. It has to be made in one step and then in another.
Oh, so
So it's basically the same thing that we did in Unit 3, where, like, for example, when we had spectator ions, we would cancel them out on both sides. You're doing the same thing here, really. Anything that's the same on the reactant and the product side, you take it out. And that's how you see what's left. All right, let's try another one. I did write your turn, so see if you can try this one. Similar question. The rate of reaction between metal ions is studied. Following 3-step mechanism has been suggested. Step 1 is the rate determining step. See if you can figure out the overall reaction and suggest the role of Mn2+. So I'll give you a few minutes to do this. What'd you say?
Obviously categories.
You said trust?
I remember like
That cannot be the explanation. Trust is not an
I
explanation.
remember like last year. I remember,
Not valid.
I remember that like last year or something like some attempts like it said suggest a role. I just put cat.
And was it right? Usually when it says role, usually it's in AS chemistry, I feel like it's either oxidizing agent, reducing agent, or
Yeah.
catalyst. It's one of those three things. Yes. For this, that is the explanation.
Even though it just says explain, because that's
Yeah,
also
it's still, yeah, they still accept it. Yes. Okay, explain.
Yeah. Yeah.
Yeah, Issa, it's the very next slide after this one is suggesting your own mechanisms. Look back. Yeah, because it's used in one step, so it's used to help it go fast. And then it's remade, reformed, so therefore it was never actually consumed.
And imagine the applications of it.
There's so many applications for catalysts.
That's me.
I mean,
I
everybody
like
might
convert.
see one.
Yeah, it's gonna show up at the end of this lesson, catalytic converters again. But they're used in a lot of different research studies. Different catalysts for different reactions. Even studying in STEM challenge, catalysts are beneficial possibly, depending on what your solution is. That's right.
About what?
Yes. Good job.
It didn't change.
All right, one more minute, and then I'm gonna go over the answers, but I wanted you to try this one yourself, just to see if you're getting the hang
What was it?
of what has to be done.
Does it go from one place to another? What is it then? Like what else? What does it do? The reaction. It's
Yeah, last one, there's something else that needs to be done.
Wait, so what I said.
Yeah, somewhere.
I'm somewhat right.
No, why? I guess
How many C is there?
Again, you can get away with just saying the slowest step for the first
How
one.
many C?
We're gonna go ahead and get to the overall equation and the role. So for the overall equation, remember we have to take out intermediates and we have to take out catalysts. So here I see an intermediate is Mn3 plus
1, 2.
and an intermediate is Mn4 plus. I also see that I have a catalyst.
Yeah.
The catalyst is Mn2 plus.
And then
The fact that I canceled it out that way means it's catalyst. And then I just add up what's left on the reactant and product side. So this would be 2 Ce4 plus, because there's 2 of the same, so you add them up. And 1 Tl, you don't have to write the one in front, tellurium plus 1. That is not. It looks like a capital, but it's not. L plus 2 Ce3 plus TL. I was just trying to curve the L, but 3 plus. That's the overall reaction. So just the roll of M2 plus. It's catalyst.
God is trust.
No, it's not true. Catalyst as it's used in step 1 and reformed in step 3. It is used in step 1 and reformed in step 3. So technically, at the end of the reaction, you still have that catalyst, but it helps the reaction go.
It's kind of just say that's the reaction side first step and then start trying to
But not trust. All right, so the final part of mechanisms, which was technically part A in the learning objectives, is how to suggest one yourself. So there is a non-zero chance on your paper 4. You could be given a reaction and they tell you to either suggest a 2-step mechanism. I've seen a couple exams where they say a 3-step mechanism for like possible mechanisms for this reaction to occur. And so what you're going to have to do is meet the following 2 conditions in the suggestion. The sum of all the steps that you suggest must add to give the overall reaction. When you cancel out any intermediates and any catalysts, you end up with the overall reaction. That's part 1. Part 2 is the rate determining step, whatever you have called the slow step, must give you the rate equation. That has to match the coefficients of the rate equation. For the rest, you're going to have to get a bit creative. You might make things you've never seen before. Because, I mean, there's a possibility they exist for, a millisecond in time as an intermediate before they decompose again. Yes, that's so.
As long as we meet those 2 conditions, is like anything correct?
These are the 2 conditions they're looking for, like for the marks.
Yeah.
So let's take a look at how creative we could possibly be.
We can make
This
this.
is our first practice question. For the overall reaction, which is NO2 plus CO goes to NO plus CO2. And given, so they have to give you the rate equation because you have to know what you're trying to match. Given the rate equation of rate equals K NO2 to the second, come up with a potential 2-step reaction mechanism, clearly indicating what is your fast step and what is your slow step. So what are the things that we know? What do we got to do? At the end, we need to come up with this. Everything has to add up to become NO2 plus CO goes to NO plus CO2. So whatever we come up with, we have to end up with that. When everything cancels out, that has to be the final response. Yes.
Do the coefficients have to be like exactly as in could it be double everything? Like
No, it has to be exact. It has to be exact. So the other thing, so I would usually make my first step my slow step. I think this is the easier pathway to go. I would write my slow step first. And then I know for my slow step, I actually know what I have to write. I know that it's got to be NO2, 2, which means I need 2 NO2 as the reactants for my first step. The way that my brain works, I actually didn't write it like that. I didn't write 2 NO2. I instead wrote it as the following. See if you follow me. I wrote it as, when I was doing this, NO2 plus NO2. Because I envisioned it as 2 molecules. How would they interact with each other? Like, how would they possibly give me, different products? So then, how could they interact with each other? What could you make as a product from NO2 and NO2? And this is all you got. You can't put carbon in here because this has to be your reactants of your slow step. It has to be this. So what could you make? ISA.
Can we make a no 3 as well?
You could. That is an option. That's not what I did, but it's an option on what you could do.
So we could have someone that has 5 bonds carbon,
Yes,
right?
but because it's just for a millisecond, it's an intermediate. So some of you are going to be very excited about this prospect.
Certainly.
Because like even try drawing the Lewis structure for NO3. That's not something that's in natural existence. It's some free radical that's going to go insane. But that's your suggestion for slow step. Okay, so now we know because that's your slow step. That has to be there, right? That matches. What are the other things we know? We know we have two NO2s and we have to get rid of one of them. So in my fast step, what are the things I have to incorporate? I know NO2 has to be on the other side. Why? Because one of these has to cancel to get my overall product. What else has to be in my fast step? CO has to go to CO2 because that's in the final product. That has to be, CO has to be here and CO2 has to be here, right? That has to be. So the last thing to figure out is what would go here. What goes here on this side? What's the missing part? Since you suggested NO3 and it's an intermediate, then NO3 has to go here, right? And it works. Your suggestion works because NO3 cancels, not in your final product. One of the NO2s cancel to give you this, and everything else is there as it's supposed to be. So yes, this is a correct suggestion for a mechanism. Yeah. Actually, that is what I suggested. That's what I ended up coming up with last night. Looking at it, I thought I came up with something else first. That's what I get. How do you feel so far about this? This is the hardest standard in my opinion, but if your brain can solve puzzles, this really is potential puzzle solving. Chemistry puzzle solving, yes.
I prefer the nitrogen monoxide. You can just ignore it.
It's here. It's in your product.
Oh yeah.
It's one of the products you needed to have. The other one was CO2. So like this cancels and this cancels. Right?
Okay.
And that gives you your final set of products. All right, let's try one for Cambridge. So this is just like a warm-up question. I don't think this Cambridge one's too hard, but let's take a look at it. The compound nitrosyl bromide. I've never heard of it.
Another question.
Go ahead.
Like nitrosyl bromide,
What if instead of using NO3 you did
nisotyl bromide.
You have to figure out a way to get rid of the O2. As long as you can figure out a way to get rid of the O2, it can possibly work.
Could you prove it?
But you have to figure out how you're gonna make that happen. Because at the end of the day, everything has to be balanced. You can't like create atoms out of nowhere unless you then get rid of them.
What if I use CH5 as an
Oh my god. All right. Compound nitrosyl bromide can be formed as shown in this random reaction. The reaction is first order with respect to NO
Gas.
and first order with respect to BR2. The mechanism has 2 steps. Suggest equations for the 2 steps of this mechanism and state which one you have chosen to be your rate determining step. So let's try this again. Everything has to add up to become this time. Where should I begin? Ramon.
Putting whatever like the first order in the first step. It's like
So
one.
I'm gonna call this my slow step. And then I'm gonna put NO plus BR2. That has to be there in the slow step. It has to be in whatever we declare our slow step to be. That cannot be any different because their order comes from this. Okay. So what can that make?
NOBR plus BR.
That's what I got. That's actually what I picked up. So NOBR plus BR free radical is what I had. Because NOBR is one of our products. So
Yeah,
what,
just it's a free radical.
but knowing that is important in general. That's what I was saying. You make something unstable, but you then use it in another step. So what would we do for our second step here?
Just do NO+VR. NO+VR.
Yes, because there's only one NO here, but there's two NOs in your final answer, right? So you've got to have another one in step two. You've also got to get rid of this bromine you just created. So NO plus BR. What do those become? That would be here. NO and Br combine, and you get NOBr. The bromine cancel, and you've got two NOBRs at the end, which matches, two NOs at the end, which matches. What's our rate determining step? The first one. You have to declare which one do we think the rate determining step. Good job.
So wait,
Yes.
does that mean you technically work backwards, like go
You
from step
can
two
work
to step
backwards,
one?
sure. Absolutely, you can work backwards. You just have to fit, like I said, the two constraints that I mentioned. As long as you fit those two constraints, you can be creative. So there's not just one right answer for these questions. All right. This is the final question on this topic, and then we go to the final thing, which is a pretty quick part of the lesson, which is called catalyst. I'm going to go ahead and turn the lights down in the back because what I mentioned before, there's going to be a time we have to quiet down for a couple minutes.
What we can have carbon dioxide.
Okay. So, last question on mechanism. Here we go. Three-step mechanism has been proposed. I give the rate equation on the side here because it's part of another question.
Yeah.
And they say, using the rate equation, which is the rate determining step?
The first one.
Why?
Because the coefficients of the reactants match the order.
Coefficients of reactants are the same as the order. That is not a lot you have to figure out for 2 marks. We have seen other 2-mark questions that are like way more work. So this is one of those things, go for the marks that you know you can get. Describe the chemical behavior of CH3CHO in step 1. That's an interesting question. What is this? Look at what's happening here. What is that doing?
It's an acid.
It's an acid.
It's another.
The answer is it's an acid. Why? That H goes right there. It donates H plus. It's an acid. OH minus is acting as a base. Not nucleophile, electrophile. It's acid-base behavior. It all connects at the end.
How's
All
that?
right. What?
How's electrophile different from acid?
It's how the mechanism takes place. If we were looking at an electrophile, we would have a different set of mechanistic behavior and not just an H plus transferring from one thing to another. Like acid base is just H plus goes from one thing to another. All right, so last topic for the day, catalysts. And so this will be one of those informational, I know how much you love the informational topics. This is the random fun facts section of the class you need to know, but could be very interesting, has a lot of important scientific applications. How do catalysts work? So review from AS chemistry first. A homogeneous catalyst is one where your catalyst is in the same phase of matter as your reactants of the chemical reaction. So if I have a chemical reaction that's aqueous and my catalyst is also aqueous, it's going to be homogeneous. If a catalyst is in a different state of matter, it's heterogeneous. So different state of matter than the reactants. So if you look at this reaction is V2O5, which is used in the contact process for making sulfuric acid. Is V2O5 operating as a homogeneous catalyst or a heterogeneous catalyst? Heterogeneous. What that means is that these gases will actually be going to the solid, like being reacted on the top of the solid. And we're going to be looking at how that actually happens, because I told you that we're going to be looking at the mode of action, which really is, how does this happen? Like how? But from mass chemistry, we learned that this was heterogeneous, and that's back as an objective for A level. Homogeneous are in the same phase. So typically, and we actually already saw a homogeneous catalyst in this lesson. I just didn't tell you it was. A homogeneous catalyst will usually involve changes in oxidation number and are typically taking place in the aqueous phase. And so, for example, here you do have a homogeneous catalyst. What is the homogeneous catalyst here? Looking at this two-step reaction. The IMAX, right? It's used in step 1 and reformed in step 2. It's in the aqueous phase, so it's a homogeneous catalyst because so is H2O2. It's in the same phase of matter. And so how can we choose what catalyst would be good for this type of homogeneous catalysis? What you have to look at is this phrase at the bottom. This is how you predict what would be a good catalyst. For whatever reaction you're catalyzing, what's important is that your catalyst has an electrode potential. Did I just say Nina 3?
Students and teachers, at this time we are in a lockdown drill. We're in a lockdown drill. I will advise when that lockdown has been lifted. Thank you. Teachers and students, that concludes the lockdown drill. Thank you for your cooperation.
Pretty quick. All right. Felt like I left that in pending basement, like the unit 3. And then we went into lockdown. Okay. So it says if we have a catalyst in the homogeneous phase, that what we will need is for it to have an electric potential that is in between that of the species that it is catalyzing the reaction for. And so if we use the electric potentials, which you would have to be given, we can actually predict if catalysis is possible, but this would not give us information about how fast the reaction is actually going. So it would not give us the value of K, for example. Yes.
Can they give us information about the metal activity series and expect us to?
So, no, they'd have to give you the numbers. They give you the numbers. And so in the standards, and I believe someone during tutoring yesterday asked exactly about this topic. Some of those random pieces of information from AS chemistry are fact, meaning that one of the catalytic reactions that Cambridge wants you to know is that NO2 catalyzes the oxidation of sulfur dioxide into sulfur trioxide in the production of something called acid rain, if you'll recall. And so how that happens is if I've got NO2, additional NO2 in my atmosphere, and I've got SO2 that's formed from industry, they'll react with each other. It'll make SO3 plus NO. And then NO that's formed will react with oxygen that's in the air and reform the NO2. So NO2 catalyzes the reaction. What phase is this in? They're all gases. So this is a gas phase catalysis. So NO2 oxidizes the sulfur dioxide into sulfur trioxide. The next step after that, which is not shown, but I'll just write it out. The next step after that would be sulfur trioxide would react with water to make H2SO4. That makes sulfuric acid. So once the sulfur dioxide is oxidized into sulfur trioxide, this is a synthesis into acid rain. And there is a non-zero chance you'd be asked to produce these equations on a Cambridge exam. It's in the standards. Now, this check up here is based on what I said about the electric potential, how a question could show up for you. It says standard pair of substances, I to IV, would possibly be able to catalyze the following reaction. The following reaction is actually similar to the iodine clock, which we're either going to do next week or the week after, depending on how the vote rolls. In the iodine clock, you actually have reactants very similar to this. And so we need something to catalyze this reaction because right now it's going to be very slow. Why would this reaction, just looking at the reactants, why do you think it would be possibly a reaction that doesn't really happen very well on its own? Because you can actually look at the reactants here and be like, yeah, I don't see how that's going to happen easily. I might need a catalyst to kickstart that. What's the issue with these reactants?
They would apply the
What's the issue with these reactants? If we think about how reactions happen, they happen because of something called effective collisions, which means they have to hit each other in the right way, in the right direction, right? To overcome the activation energy needed to go from reactants to products. So the issue, you're absolutely correct. This has got a negative charge. This has also got a negative charge. These two substances repel each other. So it's not going to be very easy for them to effectively collide to make the proper products. So what do we introduce to make this happen faster? A catalyst. And so what catalyst we choose depends on the E values for our reactants. We're given here that the standard potential value for iodine is 0.54. The standard potential for F2O8 2- is 2.01. So we would want to choose a catalyst that falls in between those. Why? Because it would be oxidized in one reaction and reduced in the other. So that's why we want it in between. So that if it's above one, it's going to be reduced, and if it's below the other, it's going to be oxidized. So which of these catalysts would work? Correct. So anything that's between 0.4 and 2.01. So the answers would be these two. We could use manganese as a catalyst here, or we could use cerium as a catalyst here. And why? The potential of these catalysts are in between the potentials of the reactants. So the catalyst would be oxidized in one step and reduced in another. So between the potential of reactants. Will be oxidized in one step and reduced in another step. And that means they'll be reformed because oxidized charge go up, reduced charge go back, down. Yes,
Will they always give us the values for the electric potentials?
they have to. There's no other way. They're not asking you to memorize those. So they have to give you the potential values for you to be able to make this prediction. So yes, they will. So homogeneous catalysis happens in an aqueous solution when the electric potential of the catalyst falls in between the electric potential of what you're trying to catalyze the reaction for. This slide right here is super quick. I was debating last night whether to even keep this in or not because I feel like you're all pretty good at oxidation. But it says here, describe in terms of oxidation number change, which species is oxidized and what's reduced in these equations. So you don't have to describe, just tell me for the first one, which of these reactants is being oxidized, SO2 or NO2? SO2, because it goes to SO3. It's literally gaining more oxygen, and you could calculate the oxidation number as well. But more oxygen means oxidized. And then what would then be reduced here? NO2. And in the second reaction, what's being oxidized? Nitrogen monoxide. And what's technically being reduced? The oxygen. Because it's going from oxygen with a 0 to oxygen with a -2 being reduced. That's why I said I debated keeping this in or not, but it showed up in this chapter, so I figured why not review. I mentioned this reaction already. And the reasoning why we would need to catalyze this, because these charges are both negative. So, because they both have a negative charge, in order for them to collide and react effectively, you would need a lot of energy to overcome the repulsive forces. So the activation energy for this reaction would be quite high. You need to probably heat it up. So instead of doing that, we can add a catalyst. Fe3 plus is one that can be chosen to do that. And so here, hopefully you will see that this is step 1, Fe3 plus. I'm missing part of it. Fe2 plus. And so here you can see that iron is reduced and the iron is oxidized back in the second step. And so that's why it would be useful, because you reduce the catalyst in one step and then reoxidize it into the form it started off with at the end. So you just have to add this in. I don't know why it didn't get caught. One more topic. And it is, I don't want to say a doozy, but it is very interesting. And it's how do heterogeneous catalysts work? So the last topic for the day is how do heterogeneous catalysts work? Like how does a catalyst work when it's in a different phase from the reactant? There's going to be a acronym that you will memorize or can memorize to help you out with what happens. But the first thing you need to know is that they take place by reacting on the surface of the catalyst. So this is, for example, how catalytic converters work, which I'll bring back up on the last slide. So the actual reactants react on the solid surface. The mechanism of how this happens, so remember, mechanism really just means how does this happen, is used with a theory called adsorption. That is not a typo. It is not absorption, adsorption. And so I have what that means here. Absorption, like absorbing, means whatever you have goes into the material. Like if I have a paper towel that absorbs water, water goes into the paper towel, right? Adsorption means that your substances stick to the surface of whatever you have. Kind of like that, yeah. So like adhesion, yes. So adsorption means that your particles are going to be sticking on top of the surface. So your gases go to the surface. And so that's what it says here. Adsorption is when molecules become bonded to atoms that are on the surface of a solid. So adsorption means bond to the surface. Adsorption means move into. So we're not looking at adsorption here, we're looking at adsorption. So how does this happen? And the textbook actually has really nice diagrams, so I printed them for you. They're in the actual textbook. It's a 5-step process. And that's why I said there's going to be an acronym that helps you remember this. The acronym is DARD. That'll help you remember the names of the steps. The first DARD with the extra D. So the way this works, and this is using the Haber process as an example, where iron catalyzes this reaction. First step, the fusion. What does the fusion mean? Like from bio, you learned what diffusion was. What's that?
Movement.
Movement, right? So the fusion means nitrogen gas and hydrogen gas are going to move. The word thing they're using for that is to the surface of the iron. So onto the surface. Once they reach the surface of iron, adsorption happens, which means that these reactants chemically bond to the surface of the iron. And these bonds that form are strong enough to weaken the actual covalent bonds within nitrogen and hydrogen, which is crazy because nitrogen has a triple bond. So the implications of this are wild, that a catalyst can do this, break the triple bond in the nitrogen, and makes the bonding weak enough to allow products to leave the surface. The next step is reaction. So the R in DARD is reaction. The reaction happens. The nitrogen and hydrogen atoms reconfigure to connect with each other. They're close enough to each other to react effectively. And then desorption happens. So desorption is the opposite of adsorption. D means that the bonds weaken, break off, and then your ammonia diffuses away, meaning moves away from the surface. So your product moves away from the surface after it's formed. So diffusion is at the first and the last thing. It's diffusion at the beginning, then adsorption, then reaction, then desorption, then diffusion. And yes, Cambridge does want you to know these steps. I think that the images in the textbook are very helpful. So they're better than anything that I had found on my Google searches. I've tried to find images on Google and I could not find anything that good. I actually think the textbook has a really nice description of how this works. Diffusion means they're traveling to the surface of the iron. Adsorption means this, that they're actually connecting with the iron. Reaction means that your new bonds form between your nitrogen and your hydrogen. That's what these dots mean, new bonds forming. Desorption means once your NH3 forms, it disconnects. And then diffusion means it leaves. The product leaves. So this is a suggested mechanism for the heterogeneous catalysis of nitrogen and hydrogen into NH3. I wanted to show you that you could look at this. I did find this one online for other reactions we've seen that have heterogeneous catalysis. This is the reaction of ethene with hydrogen to make ethane, which is with a nickel catalyst, if you'll recall, which is a solid. It's called hydrogenation, right? And so hydrogen atoms adsorb, ethene adsorbs, then they migrate to each other and link. That's the idea. And finally, we're closing up the day by looking back at catalytic converters. And so, if you recall, in a catalytic, yes.
I'm not cutting those off of other people's crosses and setting them.
I don't think that.
That's what scrap shops do, right? When people sell their cars, they sell them to scrap shops at the end, and then they like take expensive parts and resell. Mm-hmm. All right, so catalytic converter is an expensive part of your car. On that note, and I found this online, but I thought that this was a pretty good image to describe kind of what's going on. It's a coated inside of your catalytic converter in a honeycomb pattern that has platinum metal, palladium metal, and rhodium metal. So platinum, palladium, and rhodium are used as catalysts so you can actually harness the platinum out of a catalytic converter and make money. Absolutely. Yes,
So if carbon dioxide goes in my catalytic converter, it does nothing, right?
right.
Why do people use
That's right.
these nests?
So this was just, I found this online, but it pretty much summarizes what we learned last year. That if I have these harsh, dangerous gases, the catalytic converter works to change them into less dangerous gases, and this is the reaction we needed to know for that. It also oxidizes hydrocarbons into carbon dioxide and water as well. And I did want to bring up that in the standards, Cambridge is asking for you to know the names of the catalysts in the catalytic converter, all three. They want you to know that it's platinum, palladium, and ruby. And so that's it. We are done with the first half of the unit, unless you all vote to take a test just on this half. So you can either take a vote and vote for breaking the unit into two parts, or moving forward next week and starting straight into transition metals. So you have till tonight to make your decision. Look over it carefully.
You know, like, I was surprised. I thought it was gonna be the mechanisms, the thing that would involve too much chemistry. It was catalysts that involved too much chemistry.
For you?
Yeah.
So the mechanism's okay. No, I think the mechanisms made you happy.
Mechanisms, well, yeah, that too.
The reason is the